Now that we know about redox reactions and figuring out what's been reduced and what's been oxidized and oxidation states, how do we predict redox reactions? How do we predict the outcome of these? Well, that's all going to come down to something called voltage. Now, you may know about voltage. This is a very common thing. There's voltage in the uh, any kind of battery that you use, the lead acid battery in your car, the lithium ion battery in your phone, even a AA battery or the outlets in your house generally have 120 volts of electricity powering them. So when we talk about electricity, it's going to be the movement of electrons. And so voltage is going to be how much these electrons want to move. Okay? So I've got a reaction set up here. This is a pretty straightforward reaction. It's copper sulfate in solution, so it's CuSO4 in aqueous solution, plus a bar of zinc. So this is zinc metal, and it's a solid. What's going to happen in this reaction? Well, what's going to happen, I'll just tell you the outcome, is the zinc is going to replace the copper. And we're going to get this copper, it's going to be an aqueous solution, this is going to be solid. We're going to get the copper precipitating out of the solution. It's going to become solid while the zinc steadily gets dissolved into this. And so eventually all of the zinc will replace all of the copper in this ionic compound. And so we call this a single replacement reaction. Single replacement. Now, once we get started predicting these, a very common question is, how do I know what the zinc is going to replace? How do I know it's not going to replace the sulfate? Well, if we look at this, copper and zinc, these are both metals which form cations. And since this is an ionic compound, the cation needs to be replaced with a cation. So let's generalize this a little bit. If I've got the copper as an ion, well, copper and sulfate together, this is going to be copper 2 sulfate, so this is going to be copper 2 plus. And it's being mixed with zinc. This is really the business end of this reaction because the sulfate doesn't change. If we looked at its oxidation state, it's going to be -2 all the way through. Nothing about it changes, so we can kind of just ignore it in order to generalize this reaction. On the other end, on the outside of this reaction, we're going to get zinc becoming the ion and copper being a pure metal. So what happened here? Well, this zinc had 2 electrons and it gave those 2 electrons to the copper. So the zinc gave 2 electrons to this copper. When that copper received them, well, now the zinc has that +2 charge and the copper doesn't have a charge at all. It becomes a pure metal again. So what's being reduced and what's being oxidized? Well, the copper goes from a +2 charge to a 0 charge. So the copper is being reduced. So let's label that red. And the zinc goes from a 0 charge to a +2 charge. Its charge increases, so it's being oxidized. So when we look at this generalized reaction, we can actually split this into 2 half reactions. And this is going to be the key to predicting the outcomes of these types of redox reactions, these single replacement reactions. So we've got the copper 2 plus. And really what needs to happen is this copper needs to get 2 electrons, okay? It needs to get those 2 electrons in order to become copper metal. So this is a half reaction. Notice this is only half of this overall reaction. But this half reaction has some very important characteristics. And we'll get into those in just a minute. The zinc is also going to have its own half reaction. But it's going to start as the zinc metal. It's already got the 2 electrons. And then in order to become the zinc ion, it needs to get rid of 2 electrons. So this zinc needs to get rid of 2 electrons. Remember, this is the oxidization of zinc, and this is the reduction of copper. So in order to predict these, we need to look at something called a reduction potential table. So this is what a reduction potential table looks like. It has half reactions, just like what we just wrote out, and it tells us a potential. What is a potential? Well, a potential is really the voltage that this half reaction could produce. And since it's only half the reaction, if I have 2 parts of a reaction together, I'm going to combine their voltages. And so let's find copper on this. It's going to be right here. Copper 2 plus 2 electrons makes regular copper, and that's going to be 0.34 volts. So if I go onto here, I see that's exactly the same way. That's set up exactly the same way. And so that's going to be plus 0.34 volts. Now let's look for the zinc. And if we, oh, it's right up here. It's right there. If we see this zinc, notice something very important about this. This is the reduction half reaction for zinc. So that's set up differently. Let's look at that over here. The reduction half reaction would look like zinc 2 plus 2 electrons, making zinc metal. And that would have been a negative 0.76 volts. But that's not what we have over here. That's the reduction reaction. We have the oxidation reaction for zinc. So what's that going to be? How's that going to be different? Well, that's just going to be the opposite voltage. All I have to do for that is flip the sign, and it works the same way. So the reduction of zinc is going to be a negative 0.76 volts, but the oxidation of zinc is going to be a positive 0.76 volts. And now when I put these two half reactions together into a whole reaction, what's my total voltage going to be here? Well, to figure that out, I just add these together. 0.76 plus 0.34 is going to be a positive 1.10 volts. Now, this is the key to predicting the outcome of these reactions, is I'm going to have a positive voltage. This reaction is going to proceed. So if I've got zinc, a zinc plate, put into a solution that has copper ions, well, my zinc is going to replace my copper ions, and I'm going to get solid copper coming out of this. What if we flipped this around? What if we had a solution of zinc sulfate and put a copper bar into it? Well, if we did that, if I set this up, what am I going to get? Is this going to proceed? Is this copper going to replace this zinc? Well, to figure that out, I'm just going to do the reverse of this reaction. This net reaction here, the real business going on is zinc 2 plus copper trying to form Cu2 plus zinc. So I can look back at both of these half reactions. Well, I've got zinc 2 plus, and it needs to get 2 electrons, it needs to receive those 2 electrons, and it's going to try to take them from the copper in order to become pure zinc metal. And then for the copper to become a copper ion, it needs to give up 2 electrons. Well, if we look at our voltages here, again, this is now my reduction reaction. This is my oxidation reaction. This is now going to be a negative 0.34 volts. 4 volts. And this is going to be a negative 0.76 volts. Well, if I add those together, I get an overall negative 1.1 volts. Because that's negative, this is not spontaneous. So this reaction would not proceed. So on the other side of this reaction, nothing happens. Nothing happens when I put copper into this zinc solution. The reason for that is copper likes its electrons way more than zinc does. So it's not going to give away its electrons to zinc. Zinc doesn't want them. So any redox reaction we set up, we can figure out the half reactions just by looking at am I working with metals? Am I working with non-metals? What am I working with here? We can set up our two half reactions and figure out our collective voltage. And if it's positive voltage, it's spontaneous. So let's write that. Let's write that here. Positive voltage means the reaction proceeds. And a negative voltage means the reaction it means nothing happens. So in the next video, we'll set up a few examples and we'll go over this more specifically. But for now, we should be able to identify what are the pieces of this reaction that are actually participating. We should be able to identify who's going to be changing their charge. If I just give you this, you should be able to identify, hey, zinc, that's a metal, copper, that's a metal. Those two things might replace each other. You should be able to identify that. And then you should be able to identify who would be reduced and who would be oxidized. And as we practice this, we'll be able to figure out what our voltages are going to be, and whether or not this reaction would be spontaneous.